Okay, let's begin. So today we're just going to wrap up last class, do some more examples from substitution, and do some housekeeping, and that's it. We'll start to cover some new ideas tomorrow. So let's just go through some of these examples that we looked at last time. Did we do that one? I don't know. This one. Here are some examples where you need substitution to be able to do them. At least in the beginning. So what would we do here? What's the substitution? Yeah? Equals x squared. Remember, once we do that, we find its derivative. Once we do that, we can solve for dx. Once we can do that, we can plug in everything. So we have x sine u, dx would be du over 2x. The x's would cancel. You'd be able to bring the 1/2 out. So you have that. Now that one's easy. That's a rule that we already know. This just gives us the negative cosine. And then we back substitute. That's minus 1/2 cosine of x squared plus c. For this one, yeah? So that's making it complicated. So we start out by choosing that. We need to make sure that once we find this derivative, remember the way you check that you're making a substitution that makes sense. This can change a little bit, but you need to be able to find the variable part of the derivative somewhere else in the function. So that says that's probably a good substitution. And again, solve for the dx. Plug everyone in. X squares would cancel. You can factor out the 2/3. We have radical u, du. How do you integrate that? Yeah?
Leave 3/2 u. Or u to the 3/2.
Right, this says u to the 1/2, do the power rule. Add 1 to the power, you would get u to the 3/2. Divided by the new power, you multiply that by 2/3. Ultimately, you get 4/9. So this is 4/9 times x cubed plus 1, 2. And again, you can always check your answer by actually differentiating this. If you differentiated this, you'll realize that you get that. What would we do here? What would you try for this one?
1 plus root of x.
There's 1 plus radical x. Your d would be what? Derivative of 1 plus radical x. Are you raising your hand? Huh?
It's
Yeah.
1 over 2 square root of x.
1 over radical x, there's a 1 over radical x. Dx, this would be 2 radical x du. And then I would go plug these guys in. This is radical x here, this would be u squared. This would be 2 radical x du. So that cancel with that. And then I have 1 over u squared. How would you integrate 1 over u squared? Well, 2 times 1 over u squared. Yeah?
That'd be negative 1 over u.
Right, because you would write that using the power rule, so that's u to the minus 2, add 1 to the power, divide by the new power, just get minus 2 over u. And plus c. And of course, that is just minus 2 over 1 plus radical x plus c. What would substitution be here? What would this one be? Yeah? Equals cosine. Our du would be minus sine. This means that our dx would be minus du over sine of x. So go here and plug that in. Cosine is u, so that's u cubed. Times sine x times minus du over sine x. Sine x's would cancel. So we have minus the integral of u cubed du. So this minus u to the 4th over 4 plus c. This would give us minus cosine to the 4th x plus c. Can anyone figure out this one? Substitution for that guy? Ideas here?
Yeah. You distribute the radical x and then factor out x of 3 halves.
Distribute the radical x and factor out x to the 3 halves?
Yeah.
To what end?
So du would equal dx times radical x, and then if you made that, wouldn't that be equal to x of 3 halves? And if you differentiate it, it would be 3 halves x.
But I mean, if you were to distribute this would be radical x plus x radical x,
Yeah.
and then you factor what?
And that would make u equal to the x plus radical x all around. That would.
Well, how would you do that? Because I mean, even if you wrote these as powers, like x to the 1/2 plus x to the 3/2, if you were to refactor that, you just factor out the radical x again. Factor out something else, you'd end up with a negative power. If you factor out the x to the 3/2, you'd end up with a negative power over here. Let's see. I don't see how this helps. Other ideas? Kind of jumping around here, but yeah. Post that. That substitution will actually work here, believe it or not. You do du, be 1 over 2 radical x dx. So your dx would be 2 radical x du. Go over here. Here I see there's a radical x that I want to be able to cancel, so I leave this radical x there. This would cancel with that. I have the 3 times the 2, I'd be able to factor out. That becomes 6 times. What would I do with the 1 plus x? It's u squared. The antiderivative of that. Arctangent. Or tan inverse square root of x. So there are 2 inverse trig functions you should know the antiderivatives of. So you know the derivatives of them. Sine inverse and tangent inverse, you should know their derivatives, and hence you would know the antiderivatives of these expressions. So that was an arctangent to go there. And distinction. What about this one? pretty complicated to have that in the power of an exponential. Equals our tangent x, our du would be 1 over 1 plus x squared. This means that our dx would be 1 plus x squared times du. Therefore go here, plug that in, 1 plus x squared to the minus 1 e to the u times 1 plus x squared du. This will cancel it out. So end up with the integral of e to the u du, which is basically itself e to the u plus c. So that's e to the tan inverse of x plus c. About this one. So the next test and on the final, I didn't post a review yet, but I'll do that by tomorrow. Because our last test is on. So tomorrow's our last quiz. Our last test is next Wednesday. So I'll post a review by tomorrow night. But the next test and the final will include one problem where you're just computing a bunch of integrals. So it is something that you want to get really good at, and you do want to kind of practice and drill this in. So just as how on the first test there was a problem where you had to do a bunch of derivatives, and there's another problem where you have to do just a bunch of integrals. So be prepared to actually compute a bunch of these guys. The trick here is to apply a trig identity. This we know is 2 sine x cosine x. So this becomes 2 cosine squared x times sine x, which is similar to what we did earlier with cosine cubed times sine. So we would just say u equals cosine. d would be minus sine of x, so then you end up with minus u squared. So you would have minus 2u cubed over 3 plus c. So it's a minus 2 cosine cubed x over 3 plus c. There's also a definite integral in here, which I actually want to tell you a couple options of how to do with that, and then I can describe that thing I mentioned last time about trig substitution. So we had the integral from 1 to e of ln. That guy. I'll show you a couple ways to tackle it. Well, first of all, the trick was to realize that I can write this as x to the half, and using the log rules I can bring that power down. So it's just 1/2 ln x over x. Now, hopefully you'll see that u equals ln x would actually work out here, because your du would give us that 1 over x. Now we can start to plug these guys in, but we have a couple options here. So from this point on, I'm going to split this into 2 possibilities. Here's method 1. And talking about methods because we're doing actually a definite integral. So method 1 is to actually leave the old limits. I'll tell you how you want to write that down. So we can go in and we can start plugging in things here. So we have 1/2 times ln x is just u. Here we have our x, and this got to be x du. Of course, as the x's are going to cancel. But leaving the old limits, you kind of have to make sure you're not mixing them up. So you literally write an equation here, saying that your x is equal to 1 to e. And that's super important that you make that note, that the x, that the limits on your integral is the x. Okay? Because I'm leaving the old limits. The old limits were in terms of the x. These were on the x-axis. So kind of do things as you normally would. So this is 1/2 x x equals 1 to e of u du. Of course we can actually integrate that. That is u squared over 2, so this becomes u squared over 4 between x equals 1 and e. So again, I'm leaving things in terms of x. Keep writing that because you do not want to plug these numbers into u because they're not the limits in terms of u. So what you'd want to do first, if you leave the old limits, you must back substitute before plugging the limits in. Here, I would replace my u with what it was ln. It's going to be ln x squared over 4 between 1 and e. Applying the fundamental theorem of calculus, we get ln of e squared over 4 minus ln of 1 squared over 4. What is ln of e? It's 1, so that's just 1 over 4. It's ln of 1. 0. So let's get 1 over 4. This is one way you can do it. You can do method 1. Leave the old limits, do your substitution, and back substitute before plugging in the limits. So that's one option. So starting from this step, say star. From star, let's go with talking about method 2. Now method 2 says we can change the limits. So how do you actually change them? Use the substitution equation. So originally we had u equals ln x. So this will tell me how these x coordinates will behave in terms of u. So I know that when my x was 1, this means my u would be ln of 1, which is 0. And when my x is e, this means that u would be ln of e, which is 1. And so now when I start plugging these guys in, what's going to happen is I would get the integral, well, I'll get the same integral, 1/2 u du, except now I can just put the numbers 0 and 1 here. So I don't leave the integral, the limits in terms of the x coordinates, I change them to be u coordinates. And so here what you realize is that once I integrate this u to the u squared over 4, I don't actually have to back substitute because these guys are now the u values. I can just plug these numbers directly in there without changing back to x first. And so I can just plug in 1, get 1 over 4, plug in 0, I would get 0, get a quarter. Now, for the most part, this isn't too much trouble. Take you a few more seconds to write down, but in general, it's not terribly crazy. When you don't want to do method 1, as I mentioned before, is in a case like trig substitution, because this step here, back substitution, can be quite complicated for more sophisticated methods. So can be complicated. So just easily plugging in your u with ln x. It looks very simple here, because it is, but there are cases where actually being able to get your answer back in terms of the original variable can be complicated. So here wasn't too much of a big deal, but I do want you to be aware if there are other ways to do things where it might actually be beneficial. So let's actually just make a note of that here. Method 2 is, it's not the only game in town, but it's highly recommended. If doing a definite integral by a trig sub, or any method where back substituting is complicated. So here it didn't seem like a big deal, but in general, kind of getting things back to the original variable can be, can present its own issue. It's a whole other set of calculations. And so, again, when you're in Calc 2 and they talk about trig sub, remember this. Oh yeah, John told me about this. Right? You see a definite integral and you have to do a trig sub to get to it. Don't even worry about back substituting, change the limits. It will save you so much time. Because it's not going to be as easy to just jump back to the variable x. So I wanted to make sure I told you guys about that. Another good example that will come up when we talk to a lot is knowing how to integrate something like sine squared of x or sine or cosine to any even power of x. And the trick for this one, I believe I mentioned it last time, was to use the double angle formula. So it turns out that sine squared, you can remember it's 1/2 of 1 minus cosine 2x. So this would be 1/2 times antiderivative of 1 is x, antiderivative of that is actually 1/2 sine 2x. Now technically I did a mini substitution here, but it's kind of silly to write it down. So some substitutions are easy enough to do in your head, in particular when the thing you're substituting is a linear function. So star, you can realize that in general, if you want to do the integral of some function where there is something like mx plus b, you can always do a substitution. And it will look like that. If you do like u equals mx plus b. It shows up a lot in like sine and cosine, for example, so you can realize that if you wanted to integrate cosine of, say, 3x plus 7 dx, well, technically you do a substitution, but it's just going to be 1/3 sine of 3x plus 7. Or if you had to integrate the sine of pi x dx, well, that's just going to be 1/pi times the negative cosine. So those are little tricks you can use. Whenever the thing you want to substitute is linear, you can just divide by the slope and just find the antiderivative of the other function. Right? So that shows up a lot. For something like cosine of 2x, I think your Calc 2 professor would be like, if you did actually do a substitution there, okay, overkill, but okay. So if the thing you want to substitute is linear, you can always just divide by the slope. I do want to mention that this is not something that you can do in general. This is only it'll only work if your derivative is a constant. So you can actually just divide by the derivative in general. So if you saw something like, oh, e to the x squared, and you wanted to anti-differentiate that, you can't just decide to divide by the derivative and multiply by the original function. You can verify for yourself that that would not be correct. Right? So you can't just divide by a derivative. The problem here is your derivative of the power is 2x, which is not a constant. So this trick doesn't apply as long as you make sure you don't do that, which is relatively common to see students kind of do that. They want to reverse an antiderivative by dividing by a derivative instead of multiplying by the derivative because they're thinking of the chain rule. But the thing is, they forget, if you wanted to differentiate that, you use the product rule. That will break things into two terms. You won't get the original back. So be careful. You can't actually do this in general. But if you would say here, your u is equal to 3x plus 7, then that would mean your du is just going to be the constant 3. And so the constants, we can always factor them out and divide by it. And so that's why that works out here. That's another thing you want to know about. Anything else? Sorry, I don't think I want to tell you anything about computations here. So, I mean, we'll look into some applications tomorrow, but for the remainder of the class, I just want to write down some things. Technically, we've been using them all along, but I never officially stated that these things were rules that you could prove and blah, blah, blah. So, for the sake of being responsible, let me just actually mention these things specifically. So things like integrals distribute across sums and the constants out and things like that. We've been sort of mentioning it, but I never actually wrote it down. Let's just tidy things up a bit. So recall, for one, just to make this very specific, that this guy was, we referred to as the area under a curve, under f of x on the interval AB. And pretty much every time I wrote that, I wrote under in quotations. You may or may not have noticed, but what under, why is that in quotations, is because this is talking about the net area under a curve. I mentioned last time, the way we set up Riemann sums was based on the heights of our rectangles, which was given by our function. And so, let's say on the interval AB, your function did something like that, slice through a C. Then your rectangles erected here will give you all positive y values, and therefore whenever your function is above the x-axis, the integral is going to give you a positive area. So this is A1, and whenever it's below the x-axis, because your rectangles will give you negative y values, it will give you a negative area, so call that A2. So in this case, if I looked at the integral from a to b of f of x dx, it will not give me the bounded area between these curves. It will actually give me from a to c plus the integral from c to b, and this will be it'll give me a positive area, and it will actually give me a negative area for this guy. So that you have to be aware of. So every time when you find an integral and you get a number, it's not necessarily the area. You have to be aware that in the instance that your function dips below the x-axis, your integral is actually going to be subtracting those areas. So your final answer might not actually be the total magnitude of the area. It could be like some addition and subtractions going on. So you should be aware of that. I mentioned that last time, but I wanted to actually write that down specifically in general. So the integral as defined gives us the net area under a curve. So where your function is positive, it gives you positive area. Where your function is negative, it gives you negative area, quote unquote. So we'll actually deal with that tomorrow specifically. How do you go about knowing what the actual area bounded between two curves are. That's going to be an important thing we'll deal with tomorrow. Other than that, just to be, again, as I say, responsible, should mention some properties of integrals. So let f, g be integrable functions. Basically what that means is we can set up Riemann sums to find the area under their curve, and when we take the limit, it exists. It gives us a number, it gives us a value. And let little c, little m, big M be constants. Here are some important properties you want to realize. If you look at the integral from a to b of a constant, the result is going to be that. This one you can see, because if you have just a constant function that's a horizontal line, if I want to find the integral from a to b, it's clearly just going to give me the area of that. So that's going to be length times height, which is b minus a times c. That's always going to be true. State that specifically. It is also going to be true that we can factor constants out. So if I have the integral of c times a function, I can factor the c out and take the integral of the function. So we know something similar works for derivatives, it also works for integrals. It also turns out that integrals distribute across sums. So if I have one function plus or minus another function, I can take their integrals individually. Or vice versa. If I have two individual integrals and the limits are the same, I can actually compress them into one integral. We'll actually look at something like that tomorrow. So integrals can distribute across sums. We can factor constants out. They do not distribute across products, so I'm not even going to write that down. Here's one thing also. If your f of x is positive on an interval, then the area under f will be positive. In fact, there's a problem that tells us how to compare integrals. You're going to use notions like this, especially in comparison tests in Calc 2. You'll use this idea. If one function is always greater than or equal to another function on an interval, then it turns out that the integral of this function on that interval will be greater than or equal to the integral of the other one. So integrals maintain inequalities. So if one guy is bigger than another guy, the integral of that guy is bigger than the integral of that guy. And again, a lot of these follow very easily from the Riemann sums approach. If you just write these guys as summations, you can split up summations in this particular way. Another property. Suppose your f is what we call a bounded function, meaning that there's some number that it's always larger than and some other number that it's always smaller than on some interval. Then it turns out that if I were to take the integral of this interval, of course it should be, by this rule, it's definitely going to be larger than the integral of m and smaller than the integral of big M, but by property 1, we know that this guy is going to end up being m times b minus a, and then this guy is going to be big M times b minus a. So these are some properties. We've made use of like properties 1 through 3 this whole time. These are nice ideas to know. But you really make use of things like this in Calc 2. Okay, pretty much want to stop there. Tomorrow we'll look at some applications of integrals. Not a lot, just a few. Because you do a lot more applications in Calc 2. And we'll do integration by parts on Friday. Yes.
The only quiz tomorrow?
The quiz is everything up to integration by substitution. So, so just computing a bunch of integrals. I'm going to ask you to compute a bunch of integrals.
That's it.
Yeah. Because I already tested you on areas and all that stuff. And remote stuff. Yeah, just be able to compute a bunch of integrals. I'll give you a few integrals to do.
What about the previous quizzes?
What about?
I never got them back.
Which ones did you not?
The